Hi, everyone. So today we're going to start talking about the integral test and p-series in order to determine convergence or divergence of a series. So let's start with the integral test first. There are some initial conditions that do need to be met in order to utilize the integral test. So let's start with those. We have if our function f of x these are the three things that f of x needs to be: positive, okay, continuous, and decreasing for x is, whoops, let me fix that. X is greater than or equal to 1, okay, and a sub n equals f of n. So essentially, your function f of x is coming from the rule that is generating your series, right? And then we hold these to be true. So then the sum from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. So essentially, what we're doing here is we can set up an improper integral and determine whether that improper integral converges or diverges, which then tells you whether the series converges or diverges. And so then a big note here, and this is really important if you're taking the AP exam. So note, you must state all initial conditions if you're going to use this test. So be extremely careful with that, and I'll kind of model how to do that when we go through some examples. All right, let's take a look at number 1. So we have the sum from n equals 1 to infinity of 1 over n squared plus 1. And so that means our function f of x is going to be 1 over x squared plus 1. Okay, well, this function needs to meet our initial conditions. Is it continuous where x is greater than or equal to 1? Well, yeah, it is. There's no discontinuities. So it is continuous. Is it positive from 1 to infinity, inclusive, right? Yeah, it is, right? It's always going to be positive. So it is positive. And is it decreasing? Well, as we go from 1 to infinity, that denominator is getting larger. So 1 divided by bigger and bigger and bigger numbers, it is in fact and decreasing on the interval from 1 to infinity. So check, we are able to use the integral test. Note, it's annoying. You have to write down those initial conditions in order to use the test. So write down f of x, what it is, show that it's, or state that it's positive, continuous, and decreasing on the interval. Okay, so now we're going to set up our improper integral. So we have the integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, remember, to calculate this, we can write this as a limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1 dx. Okay, from here, we're going to take the integral of 1 over x squared plus 1. We should be fairly familiar with that by now. That's our arctangent. So we have the limit as b approaches infinity of arctangent of x, and we're evaluating that from 1 to b. So then we have the limit as b approaches infinity of arctangent of b minus arctangent of 1, or inverse tangent, however you want to write that. Okay, well, inverse tangent. Graphically, we actually know that inverse tangent has a horizontal asymptote, right? So it kind of looks like this S shape on its side. And as b approaches infinity, as we move to the right this way, we're actually going closer and closer to pi over 2. So this would equal pi over 2 minus, and the inverse tangent of 1 is pi over 4. Pi over 2 minus pi over 4 is pi over 4. Well, guess what? This improper integral converges. So then we actually know that the sum, so therefore, the sum from n equals 1 to infinity of 1 over n squared plus 1 also converges by the integral test. Oops. You can abbreviate this as IT as well. Okay, so now's a good point in time to go ahead and pause the video and try numbers 2 through 5, and then you can unpause and go through them with me. Okay, so let's take a look at number 2. We are finding the sum from n equals 2 to infinity of 1 over n times the natural log of n. Okay, so first we need to establish our initial conditions. So f of x in this case is 1 over x times the natural log of x. All right, and we need to show or state that this is continuous, positive, and decreasing. Okay, from 1 to infinity. Well, okay, so we have, it looks like we don't have any discontinuities from x equals 1 to infinity, because the only one would be at 0. So it looks like it is continuous. Is it positive? So let's take a look. We have, yeah, it looks like we're going from 1 to infinity. We're going to have all those values in the denominator are going to be positive. And that denominator is just going to keep getting larger and larger. So it is also decreasing on our interval from 1 to infinity. Okay, so check, right? We've met our initial conditions. So now we can set up our improper integral, the integral from 1 to infinity. Our lower bound in this one's 2. I didn't quite catch that. So actually, sorry about that. We want to make our interval from 2 to infinity. And so actually, same idea here. It's from 2 to infinity. Right. And actually, they did that on purpose because I just realized natural log of 1 is 0. So that would not be continuous. So sorry about that. But yeah, it just needs to be continuous, positive, and decreasing on the interval that it actually gives you for your lower and upper bound of your series. So yes, from 2 to infinity, those hold. Sorry about that. I was just going through the motions too quickly. Okay, so we have the integral from 2 to infinity of 1 over x times the natural log of x dx. And we're going to go ahead and take that integral. Okay, this one is actually not too bad. We're going to be able to use u sub, but before we do that, I'm going to rewrite this as the limit as b approaches infinity of the integral from 2 to b of 1 over x times the natural log of x dx. Okay, so we're going to use u sub, so we can let u be the natural log of x because the derivative of natural log of x is 1 over x dx, which we actually have in the formula. So then we end up with the limit as b approaches infinity of the integral. Now be careful, you do need to change your upper and lower limits of integration. So we have natural log of 2 to natural log of b, and then 1 over x dx is going to get subbed in with du. And so we just end up with 1 over u times du, or just du, which equals, you can think of this as u to the negative first power, right? So we have the limit as, oh, actually, no, we don't want to do that because this is actually a much easier integral than we need. Okay, so we have the limit as b approaches infinity of the integral of 1 over u is the natural log of the absolute value of u. And we are going to evaluate that from the natural log of 2 to the natural log of b. And then we have the limit as b approaches infinity of the natural log of the absolute value of the natural log of b, it's a mouthful, minus natural log of the absolute value of natural log of 2. Okay, well, what happens to natural log of b as b approaches infinity? Well, natural log is an increasing function. It increases really, really slowly, but it still is going to go off to infinity. So this entire portion of your limit is going to go approach infinity. And then you're subtracting off natural log of the absolute value of natural log of 2. It's not going to change much. So this actually equals infinity. It means that it does not exist. So this means that the sum from n equals 2 to infinity of 1 over n times natural log of n actually diverges by the integral test. Okay. Let's go ahead and take a look at number 3. So number 3, we have the sum from n equals 1 to infinity of 1 over n. So we have f of x, which equals 1 over x. And so this function, let's make sure it meets all of our conditions. So is it continuous from 1 to infinity? It looks like we're good. So it's continuous. And remember, we're matching the limits of, well, it will be limits of integration, but your upper and lower bound of the series. So remember, the other one was 2 to infinity. This is back to 1 to infinity. Continuous, is it positive? It looks like it is, right? And we're plugging in values from 1 to infinity, so it is positive. And it is decreasing because that denominator is just going to keep getting bigger and bigger, making the whole thing smaller. And that's on the interval from 1 to infinity. Check. Our initial condition has been met. Okay, so now we're going to set up our improper integral. We have the integral from 1 to infinity of 1 over x dx. Okay, we're going to rewrite this as as a limit. So we have the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Once again, not too bad of an integral to have to do. So the integral of 1 over x is just natural log of the absolute value of x, and we're going to evaluate that from 1 to b. We end up with the limit as b approaches infinity of natural log of the absolute value of b minus natural log of the absolute value of 1. Well, this is the same kind of situation, right? So the limit as natural log of b as b approaches infinity, right, of natural log of b, that goes off to infinity, and we're subtracting off 0, which isn't going to change anything. So this does not exist. It diverges, right? So therefore, the sum from n equals 1 to infinity of 1 over n diverges by the integral test. And it turns out that this series actually has a special name, and you don't have to do all this to do this type of problem, which we're going to find on the next page. Okay, so number 4, we have the sum from n equals 1 to infinity of 1 over the square root of n. So therefore, f of x equals 1 over the square root of x. And in this case, yes, it is continuous. It is positive, and it is decreasing on our interval from 1 to infinity. Check. We've stated our initial condition. We can set up our improper integral. All right, I'm going to do a couple rewriting things here. We're going to do the limit as b approaches infinity of the integral from 1 to b. I'm also going to rewrite this as x to the -1/2 dx, just to make it a little easier to integrate. So we have the limit as b approaches infinity of, now we have x to the -1/2, so we end up with adding 1 to -1/2 is a half. Dividing by a half is just 2x to the 1/2, right? And now we're going to evaluate that from 1 to b. So we have the limit as b approaches infinity of 2 times b to the 1/2 minus 2 times 1 to the 1/2. Okay, well, the square root of b, right, as b approaches infinity, yeah, it doesn't grow fast, but it will go to infinity. So this equals infinity. It doesn't matter, I'm subtracting 2 from infinity. It's not going to make a difference. Does not exist. Therefore, the sum from n equals 1 to infinity of 1 over root n diverges by the integral test. All right, last one, number 5, we have the sum from n equals 1 to infinity of 1 over n squared. So once again, we're going to write out f of x, which is 1 over x squared. It is in fact positive. I know I'm going a different order, continuous, and decreasing on our interval from 1 to infinity. Check, right? So now we're going to set up our improper integral from 1 to infinity of 1 over x squared dx. We're going to rewrite that as a limit, the limit as b approaches infinity of the integral from 1 to b. I'm going to rewrite this as x to the -2nd dx. Okay, so now we're going to integrate. We have the limit as b approaches infinity of the integral of x to the -2nd is -1 over x. And we're going to evaluate that from 1 to b. So you end up with the limit as b approaches infinity of -1 over b minus negative turns into a plus. 1 over 1 is 1. Well, as b gets really, really large, this actually goes to 0. So this equals 1. So therefore, the sum from n equals 1 to infinity of 1 over n squared converges by the integral test. Okay, so you're going to get really mad at me because it turns out that numbers 3, 4, and 5 are all can be done in a much easier way if you know what a p-series is. So let's go ahead and jump into p-series. Okay, so p-series. If p is a positive constant, then the sum from n equals 1 to infinity of 1 over n to the p equals 1 over 1 to the p plus 1 over 2 to the p, right? So on and so forth. This is a p-series. And so it turns out it depends on what p is to note if this converges or diverges. So in examples 3, 4, and 5, those ones that I circled are all p-series. Okay, so here's our p-series test. So if you have a p-series which is of the form, the sum from n equals 1 to infinity of 1 over n to the p. Well, guess what? If p is greater than 1, now actually, let's take a sneak peek at those three tests. Now notice 1 over n to the first was number 3. 1 over n to the 1/2 was number 4. Those both diverge. Number 5 was 1 over n squared. That one converged. So if p is greater than 1, then the p series converges. Okay. Now, if p is between 0 and 1, obviously not 0, because then it's not a p series anymore, but including 1, the p series, whoops, diverges. That was numbers 3 and 4, right? They fell under that category. Okay, so much easier. If you know this test, you don't have to do the whole integral test, but you can do the integral test because it also works. Okay, the harmonic series. This is a special series that actually on the AP exam, you can state by name diverges. The harmonic series is just a p series where p is 1. So it's the sum from n equals 1 to infinity of 1 over n, which would be like 1 plus a half plus a third plus a fourth, right? And so on. And so this series diverges, and it can be referred to by name to justify the divergence. So you can say that it diverges because it's the harmonic series on the AP exam. Okay, we got a couple examples. So let's look at number 1. We have 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus 1 over 4 root 4. So let's go ahead and write this in series notation. So this would be the sum from n equals 1 to infinity of 1 over n root n. Now, let's actually write this in p series form. This is just the sum from n equals 1 to infinity of 1 over, well, what's n times root n? Well, it would just be n to the first times n to the 1/2. We add those exponents, so we get 1 over n to the 3/2. Well, p in this case is 3/2, which is greater than 1, right? So what do we know about a p series where p is greater than 1? Well, we know that it, what? Converges, right? So therefore, the sum from n equals 1 to infinity of 1 over n root n converges by the p series test. And note, this is our justification right here. Okay. You do need to have that on your paper and probably the steps coming up to how you got to that, right? Okay, let's take a look at number 2. So this one, we're also going to have to do a little creative rewriting. So we have the sum from n equals 1 to infinity of n cubed times the cube root of n to the negative 11th power. Okay, let's rewrite this. We have the sum from n equals 1 to infinity. N cubed we're going to keep in the numerator because it's a positive exponent. Then I have the cube root of n to the negative 11th power. Let's move that in the denominator so the exponent becomes positive. But remember, cube rooting is the same as raising it to the 1/3 power. So this would be n to the 11 thirds, right, in the denominator. And so what you could do after that is you can think of this as sum from n equals 1 to infinity of n to the 9/3, right, over n to the 11/3. When we divide exponents with the same base, we subtract them. So think about, it would be a negative exponent, but you can leave it in the denominator as a positive one. So this ends up as 1 over n to the what? Let's see, 9, 10, 11, 2/3. Okay, so this is a p series where p equals 2/3. And that means that it's between 0 and 1, right? Therefore, p is between 0 and 1, which means that the sum from n equals 1 to infinity of n cubed times the cube root of n to the negative 11th power, it diverges by the p-series test. So some of these are a little sneaky. They are p-series, but you have to do a little bit of rewriting to get them there. Okay, that is it for today's video. Thank you so much.